Good afternoon, ladies and gentlemen. Welcome to Physics 30, EMR, Electromagnetic Radiation, Lesson 11, de Broglie and Matter Waves. Is light a particle or a wave? This was a big question that occupied many theoretical physicists for many years. There's lots of evidence both ways. For wave properties, we have Huygens wavelet theory that led to Poisson's bright spot. Of course, Young's double-slit experiment and Maxwell's EMR theory all pointed to light being a wave. But there were particle proponents too. Newton's explanation of reflection, we didn't talk about it in class, but he talks about it being a particle. Planck and quantization, photons of energy. Einstein, the photoelectric effect, and the Compton effect all point to light as a particle. Now, that leads to the interesting conclusion. Light is both a wave and a particle. We say light exhibits wave-particle duality. In some situations, it behaves like a wave, and other times it behaves like a particle. Sorry, I must improve my grammar. So sometimes it's a wave, sometimes it's a particle. It was Louis de Broglie, 6 of spades, suggested that all matter exhibited wave-particle duality. Now, it's actually really quite interesting. He said if momentum is frequency times Planck's constant, or frequency divided by wavelength, then everything has a wavelength. The wavelength is Planck's constant divided by its momentum, or h divided by mv. Now, the double-slit experiment with electrons proved that electrons behave like waves. Remember that weird quantum video I showed you? Yes. So, to see this wave behavior in matter, the mass must be very small. So, for example, what is the wavelength of a 1.3 kilogram softball moving at 3.2 meters a second? Well, here, wavelength, sorry, change colors. Wavelength equals h over p, which is h over mv. In this instance, this is, now remember, it has to be joule seconds. Electron volts, 6.63 times 10 minus 34 joule seconds, divided by 1.3 kilograms times 3.2 meters a second. That gives us a wavelength of 1.59 times 10 to the minus 34 of a meter. Now, we're never going to see this because the wavelength is much, much less than the scale of the particle. So this is going to be definitely a particle behavior. So if we shoot softballs through double slit, we'll get two lines, not a wave interference pattern. Now, so far so good. Now, on the other hand, what's the speed of an electron with a wavelength of 700 nanometers? Well, momentum is h over wavelength, or that's mv. So velocity is, rearranging this, we get, h divided by mass times wavelength. So here the velocity is 6.63 times 10 to the minus 34 joule seconds. Mass of an electron, 9.11 times 10 to the minus 31 of a kilogram. Set now 700 nanometers, that's 700 times 10 to the minus 9 of a meter. That is a velocity of 1.04 times 10 to the 3 meters a second. Now, that's a kilometer a second. We've done enough acceleration calculations involving electrons, and you realize that's not that fast for an electron. Now here I want to point out the wavelength is much, much bigger than the scale we're using. So this will be, so the electron will behave like a wave. That is 700 nanometers. If you're looking at versus 9.11 times 10 to the minus 31 of a kilogram, yeah, it's a lot bigger. 700 nanometers is a lot bigger than 9 times 10 to the minus 31 of a kilogram. So you are going to see this behaving like a wave. And go back to the electrons in the double slit experiment, you've got an interference pattern. Okay? Really neat and kind of freaky. So, last question, and seriously, this is it. Find the wavelength of an electron that has a kinetic energy of 3 times 10 to the minus 16 joules. Well, E sub k is 1/2 mv squared. Squared equals 2 E sub k over m. 2 times 3 times 10 to the minus 16 of a joule over 9.11 times 10 to the minus 31 of a kilogram. Velocity is 2.57 times 10 to the 7 meters a second. Now that's velocity. What's its wavelength? Okay, now how would you do that? Well, what's our formula? Momentum is, what was I saying? Oh, sorry. Read my own notes, Mr. Sutton, is actually quite helpful. Wavelength is Planck's constant, thank you, divided by momentum, which is Planck's constant divided by mv. So, first question is, what's the wavelength? Sorry, what's the velocity? From that velocity, we have to figure out the wavelength. So, let me see. 9.11 times 10 to the minus 31 of a kilogram times 2.57 times 10 to the 7 meters per second. And I forgot that is 6.63. Not mass of an electron. Times 10 to the 7 meters a second. 6.63 times 10 to the minus 34 joule seconds. And what's that wavelength? Well, I got 2.8324 times 10 to the minus 11 of a meter. All right? So, this is de Broglie. Everything has a wavelength. Everything acts like a wave. And everything acts like a particle, just to confuse you. All right? So, if it's really small, it acts more like a wave. If it's big, it acts more like a particle. And in between, it gets kind of freaky. So that's it for me. Try the homework questions. And if you have any questions, problems, see me in class. Otherwise, good luck.